One annoying bug I had when I was a naive younger programmer was that foreign keys in some database table might refer to a record ID that no longer exists. To put that into context, here I have a product model, and you can see that it has a NotesPack ID field, which is set to 60. And then thanks to the ORM, I can also instantiate that NotesPack object by just calling NotesPack on that product. And here we see it. Now, let's imagine I want to set that to a non-existent number. So I use Rails to find the highest NotesPack ID in my system. That's 834. So I'll just pick an arbitrary number bigger than that. Let's say 9,999, and then save it. And boom, you see that I'm unable to save that due to a foreign key constraint, that the NotesPack ID 9999 is not present. That is exactly the kind of error I want, and it prevents a whole class of failures from ever happening in my codebase. Let's say that some part of my application, for example, code in my admin area, generates the SQL statement to delete the notes file with ID 17133. Should this operation be allowed to go through? In general, there may be some sort of restraints and checks within the Ruby world, but depending on how the code is executed, on what flows and controllers it runs through, these checks may or may not get run. The ultimate way to prevent overeager deletion of this record, deletion that would leave other records in a lurch, is to use foreign key constraints. And you can see here that this delete operation failed because a constraint in the products table references this particular notes file. This is because, as you can see on the website here, each product has a best notes file, something that they display on their product page, and that's what generates this large PDF sample that you see. And a product contains many notes files, one of which is elevated to this kind of special place as best notes file. And in the case of the notes file we just tried to delete, this one was in fact the best notes file for the product it was contained within. Therefore, we shouldn't be allowed to delete it without elevating another one to that position. And the database constraint assures us of that. If you see here that we change the best notes file to something else, then the deletion will go through. i.e., the constraint helps us when it's needed, but gets out of the way when its job is done. Database constraints can be used to replace code that's involved with creating entire features, particularly ones involved with resource allocation. Case in point, here's a PHP application involved in booking medical appointments. Each appointment requires a ticket, and that ticket should be unused in order for the appointment to be booked. You can see that an exception will be raised if a ticket is used. Otherwise, an appointment gets created, and in code that's not shown here, that ticket is marked as used and then saved. In order to cancel an appointment then, we have this cancel booking function, which essentially sets the appointment tickets is used field to false, saves it, then deletes the appointment. This is necessary to free the resource. Unfortunately, this adds some complication because you have to remember to always deal with this Boolean with any actions involving the using up or freeing of that ticket resource. There is, however, a much simpler way to do this by using a foreign key on ticket ID and making that foreign key unique. Here's the new and improved code for the book method. You'll notice there's no need to manage the ticket is used Boolean. In fact, that whole column has been deleted from the database. This shorter version of the code does the trick. Similarly, the cancel booking method is greatly simplified. In fact, all it does is delete the appointment, because by deleting that appointment, the ticket ID will be freed. Let's make this a bit more concrete by visiting the database. So I'm going to check out what the first appointment in my database looks like. And you can see it has ticket ID equals 1. Let's remember that and try to reuse that ticket and see what happens. In fact, first, let's attempt to create an appointment without using any ticket, because that might be the first way the constraint that an appointment requires a ticket could perhaps be broken and the practice ending up shortchanged. You can see here that, as expected, you get an error about ticket ID violating not null constraint. That's good. It means it's impossible to create an appointment without a ticket ID. Next, let's attempt to use, or rather reuse, the ticket ID number 1. This fails, and it should as well. Key value violates unique constraint, appointment ticket ID unique. This shows us that it's impossible for someone to reuse the same ticket on another appointment. And if you watch me delete the original appointment you saw up above, then I can run that code for inserting and creating a new appointment with ticket ID 1, and it will work. For me, this is much more robust and reliable than anything involving the management of a Boolean, not to mention much less code. Validations at the Ruby or the web app level are rubbish when it comes to uniqueness. So you can see here that I have a uniqueness validation on invoice number. That is very important to be unique, otherwise there's going to be a serious irregularity in my accounting. So if we go into the Rails console and check out what happens when we run that validation. This gets run whenever you update or save a record. So now we're going to try it with the invoice number from the previous invoice. The current one is 2005.32. So let's just subtract 1 from that last number and make it 31. This should fail, and it does. But the more interesting part is the SQL queries that get run. You can see that the first one is seller load. We don't care about that one, but the next one is seller invoice exist. And what this one does is check if there exists an invoice number 2020-531. i.e. an SQL query gets run and the Ruby app has to wait for the results before deciding on whether or not the uniqueness constraint works out. Of course, you can have multiple threads or multiple servers acting on the same database. Therefore, this is vulnerable to race conditions. And over a 10-year period, I have seen this happen multiple times, and they are very surprising and difficult to debug. The kernel of the problem is that there is a time delay between when you query for uniqueness and when you actually do the write. And by the time you actually do that write, in that intervening 100 milliseconds or even a second in some cases, some other process or server will have taken up that identifier. And by the time you write, it will no longer be unique. And if your constraint is only at the programming language layer, for example in Ruby or Python, then there's no guarantee of actual uniqueness. You can, however, completely avoid this issue by adding a uniqueness constraint in the database. You can see by looking at my schema that I have already added one. It's the second of the indexes. A unique index acts as a constraint. Uniqueness constraints are important in many-to-many tables, in pivot tables. Without them, you can end up with a lot of duplicate data that is confusing and also causes bloat in the sense that the data set gets larger, and also slowdown because a larger data set takes longer to traverse. Let's make this concrete with an example from my codebase. I have a taxon and a product model. These two have a many-to-many relationship. You can see that represented in the Rails world with has and belongs to many appearing in each of these classes. This makes sense. A product could be tagged with law and with undergraduate, and similarly a tag for undergraduate can contain many products. This connection is represented in the products taxons table, which just contains a product ID, taxon ID, and a regular ID. Now I'm just going to grab the first product and the first taxon, that's arbitrary, and then I'm going to create a connection between them in Ruby using the shovel operator. And I'm going to repeat this a couple of times, basically pushing the taxon into the product's current list of taxons a few times. Now that I've run this, I'm going to move to the SQL database, to the Postgres database, and have a look at the records that are created. The ID for the product I worked with was 26 and the taxon 2. So let's check records that have both of them. And as you can see here, there are 4 records corresponding to the 4 times that I pushed that taxon into the product's list of taxons. Yet this contains no extra information, or no extra information that's valuable in this context. The naive way to avoid these kind of problems is to check whether a product's list of taxons already includes the taxon you want to add. The problem with this approach is that you have to remember to do it in every part of the code base that modifies that list of taxons. This is error prone, especially when there are multiple people on the project. A better way to do this is to create a unique constraint that spans those 2 columns. Now, once we try adding a taxon to a product's list of taxons a second time, we get an error. Specifically, we get a PG unique violation and duplicate key value violates unique constraint. That's much better. That's all I have to say on this aspect of data integrity. So see you next week.